We'll go to current slide. And again, I'll ask the question. Any questions? Anything we've covered so far? All the classes on operating, anything like that. Okay. I think we did most of this last time, but I think they're repeating some of it, and we may be repeating some. But let's go. There's no question. So, if you're on, have a ray fixed at the origin, the initial point of that ray is fixed at the origin. Here we come. Okay. No agree. Okay. And your other last name, first name, or whatever. Caitlin, got you. Okay. Oh boy, she's here. Okay. Okay. All right. So, if you've got an array, initial point of it is at the origin, okay? And you swing this around counterclockwise, okay? And you go a full 360 degrees. That would be, if you go full circle, it's 360 degrees, half a revolution, just over to the other side, that's 180. A quarter of that would be upright, that would be 90. This is in degrees now. Now, we know that, right? We also know that if you're in radians and went all the way around, how far do you go? All the way around radians is 2 pi, okay? I like 2 pi, okay? Better than 1 pi, okay. That's one complete revolution. So, guess what? The angle you go through, sweep is the same, it's just how you're measuring it, degrees or radians. So you know that 360 degrees has to be the same as 2 pi, which also means that 180 degrees is the same as pi. That ratio, that thing that you know is always true, we're going to use when we're going to be converting back and forth between radians and degrees. Okay? Now, it's okay if you want to do it this way. And they have their little conversion rules, and it's okay to use those. If that's what you understand and like to do, that kind of stuff, go for it, by all means. But I'll show you the way I think through it, because I don't like to memorize rules. I don't know. I just have never been a memorizer. I really don't like memorizing. So, let's see. Get. Is it Jemiah? Huh? Say it one more time. Okay. Are you just adding the class? Oh, okay. I was going to say, I didn't think I remembered you. Okay. The last name is Dean, D-E-A-N? Okay. I was saying, I can't find you here. Okay, here we go. Okay, and spell your first name for me. S. That's what? S-Y. R. E. N. T. Okay. T-H. I-A. T-H-I-A. Okay. So it's Cerinthia? Okay. What do you go by, Cerinthia? Okay, good. All right. I'll try not to confuse that with Jake. Okay, never mind. That's right before. Okay. All right, good deal. Okay, now, since we do have someone new in here that hasn't been here before, let's do a little flashback here. Let's first go back to, let me first do this. I teach using a package called Screencast-O-Matic. What it does, it records everything I say that's within sound of my computer here anyway, and everything that's projected on the board, whether it's from the PowerPoint or something I write on the board, because I have an ionizing pen here that I can actually write on the screen, and it gets recorded as well. And then after class, I upload that to YouTube, and it takes a while to do that, and then sometime later in the day, I will then move it in YouTube to my playlist. Okay, so hang on to that thought. So that's now to go to Blackboard. Okay, you're familiar with Blackboard, right? Okay. In Blackboard, when you go to the home page for this class, you'll know there's a bunch of blue tabs on the left-hand side of the page. This year with Blackboard, they grouped them together somewhat. Okay, I don't know why, but it's made it different, so you have to get used to it. Somewhere about the third or fourth one in the first grouping says syllabus and book information, or something like that. If you click on that, there's the syllabus for this class. And I found out last Tuesday, I also put the syllabus for this class in my linear algebra class. Duh. By mistake. I got that correct. So you could go there if you want to know. Oh, it's changed. Okay, so there's where the syllabus is. Now the tab right under that blue tab says instructor information and office hours, or something like that. You click on that one, you'll see my locator card, which shows when I'm on campus, when I'm off campus, which campus I'm on, when I'm in class, when I'm out of class, when I'm at lunch, you know, all that kind of stuff is there the whole week at a time, one glance. Okay. Also, it has my phone number and email and that kind of stuff. It's on the syllabus as well. Okay, so those are those two. Go down to the second grouping, and near the bottom of that group, about 2/3 of the way down, you'll see one that says handouts, PPTs, as PowerPoints, and more. Okay, and here's what's there. The first thing you see when you click on that one, you'll see a whole list of things. The very first thing you see is the YouTube video link. So if you click on that, you will, okay. Explain a little bit there. I keep the videos from the previous term, okay? And only when I cover the material in this term will I take off the one from the previous term. The first day of class, which was last Thursday, a week ago, my wife had outpatient surgery, so I couldn't be here. So I left the directions for the class to look at that video. There's actually two of them. The first one said syllabus, and the other said research or safety or something like that. So if you watch those first two videos, they're from last term, so the dates and the hours and things like that may be a little off, but the content is the same. Okay, so they're there. But the actual syllabus, the up-to-date one, is back here at the top. But if you want to hear me talk about it, it's there. The research paper, it's there. Okay, and I'll talk about it. And then my locator card from last term, which isn't much different from this term, and then safety issues. Okay, so you can listen to all that. Those are those two videos. They may not be the first two, but they're near the top. The one for last class, because I added that last, that's at the bottom. So if you want to know what we did last time, Tuesday, when we were here, that's down there at the bottom of that list. So every time, you know, I'll be putting something else at the bottom and probably taking something else at the top, but I'm going to leave the syllabus and stuff there. Okay, so that's the first thing you hit under handouts, PPTs, and more. The next thing you hit is research paper instruction. You can hear me talk about it in the first or second video, or you can just read about it and that is up to date. Okay. Then I think the next thing you see are all the PowerPoints we could possibly do in this course. Okay. We may not hit them all, but all of them are out there that we'll do. Chapters 4, 5, and 6. Okay, in the text. All the sections that each have a video. PowerPoint. Okay, after that, there are a few files there that, web links that either I have found or students have told me about they found helpful for the class, so you can use those if you want to. They're completely up to you. There's some other resources you can use. I think that's about everything there. Okay, so that's how you can find out what we did last time. Okay, and everybody can review what we did last time. And that's where we talked about one right around the circle is 2 pi, and we did last time also one time around the circle is 360 degrees. So those are the same. So we use this ratio. Now, what the book does is give you little formulas, and when you do this, and this. I don't like memorizing formulas any more than I like marking. So Cody, no, I'm sorry. I know you're in here. There you are. Okay. All right. Good deal. So here's their rules, and then I'll show you how I do it. I'll actually do it with the examples. This is fine. These are all absolutely correct, but I'll show you how I do it next. To convert degrees to radians, multiply degrees by pi radians over 180 degrees. To convert radians to degrees, multiply radians by 180 degrees divided by pi radians. The thing is, these are called, they have a name, what do they call it? Unitary ratios or something like that. These are the same. Pi radians is the same as 180 degrees. So that is like 7 over 7. It's 1. Well, this is not the same units, but this is how you convert the units. So I call them conversion factors. To apply those two conversion factor rules, use the basic relationship, pi radians is 180 degrees. That's what I use. Just that. I don't try to memorize which one you put on top. And I'll show you how to do that in just a minute when we get to the example. But here again, remember when we did this last time, one full circle, let's start here. One full circle is 2 pi radians. One full circle is 360 degrees. Half a circle is pi radians. Half a circle is 180 degrees. That's where we use our conversion. A quarter of that, or exactly half of pi, would be pi halves, and half of 180 degrees would be 90. Those are good old right angles. Okay? That symbol means right angle. 90 degrees. Pi halves radians. Okay? Let's go back to this one again. 1/3 of pi, if you split this in equal thirds, that 1/3 of a pi is exactly 60 degrees, because a third of 180 is 60 degrees. Go back to the pi halves here. Exactly half of that is pi fourths. Half of pi halves is pi fourths. Half of 90 is 45. So get used to these. Get to know them as if they're your cousins or something like that, okay? And then go back to this one. Half of pi thirds is pi sixths, and half of 60 is 30. These are our favorite angles of all time, and we'll use these a lot whenever we can. Of course, not all of nature gives you these, but when you can use these are the ones to keep up with. 0 pi thirds, pi 6 are 30 degrees, pi fourths are 45 degrees, pi thirds are 60 degrees, pi halves are 90 degrees, and of course, pi is 180 and 2 pi is 360. Get to know them, okay? Get used to them. They'll be your friends. Very good friends. Okay, when no units of an angle measurement are specified, that means you're dealing with radians. Now, I think what they've just done is skipped example 3 and 4. Oh, no, they haven't. Not yet. Okay. So when no units are listed, that means radians. If it didn't mean radians, what would it have to have? That little degree circle. Only if it has that degree circle, or they talk about degrees. If it's just a number, that means radians. You could have theta equal 2 degrees. That's a tiny little angle. But if it doesn't say degrees, that means 2 radians, which means a big old angle. Okay? Something just short of 120 degrees. So big difference there between radians and degrees. Which means, and this is jumping ahead, when you're doing calculations, make sure, if you're using a calculator, make sure you're in the right mode. Your calculator has a mode button or key or something, and be sure if you're dealing in degrees, you're in degree mode. If you're dealing in radians, you're in radian modes. A lot of your calculators will show that on there. Scientific calculator is really good about having RAD or DEG. Those fancy, expensive calculators, it's not completely obvious. You have to check and see what mode you're in. So, graphing calculators. Now, telephones, I know a lot of you probably will be using those. You have to know your own system. I think the iPhones and the Verizon phones, or whatever the other brand, they may have slightly different ways to identify. So you'll have to know your own syntax, basically. All right, so here's example 3. Now they, again, I hate it when they do this. I'm going to pretend, okay, let's just use this slide right here. Then we'll come back and let them do it. What they are doing is working the problem for you and saying, see, this is how you work the problem. Well, let's just do them ourselves. What we want to do is take 135 degrees, and we want to convert that to radians. Okay? So we want to multiply this by something. And it's actually going to be a blank blank something. And what you're going to get is a blank answer, and that's going to be in radians. Now understand, radians is really not a unit. I'm just writing it that way so you'll know what we're talking about. Because radians is a ratio, it is the dimensionless quantity. But we're going to put RAD for radians. Okay? Now, this is not unique to trig or anything else. I do physics and physical science and lots of things too. This is how I do all my conversions. Every one of them. Math class, physics class, physical science class, whatever class I'm doing, this is how I do the conversion. Notice I put what we're given. And I put a blank blank for what the conversion factor is, and then a blank with whatever I'm going to. Okay? Now, what's the blank blank? The first blank is for numbers. The second blank is for units. Always put the units in their place. Put the units there first before you mess with the numbers. Okay. Now, looking at this, hopefully you can see, if I'm going from degrees to radians, then one of those is on top and one's on the bottom. You decide which goes where. What must go where? Between radians and degree, one's on top, one's on bottom. You tell me what to put where. Anybody? Radians on top and degrees on the bottom. Why? Because the degrees are going to cancel out and you're left with radians right where you want it. Right? So that's how I do first. Always put the units into place. Okay? Now, match the number with the unit. How many radians is how many degrees? That's all you need to know. How many radians is how many degrees? You tell me. Oh my. It was doing it. Second, pi radians is exactly 180 degrees. That's all you need to remember. Okay, now at this point, just do the math. Okay, you see the degrees are going to cancel out. Get rid of those. And let's say I know 5 will go in 135. That will go to 27 times. 5 will go into 18. 36 times, isn't it? Oh, what will go into 27 and 36? All right. Let's see if I can make a guess here. Jemiah? All right, good deal. All right. We're doing example 3 in the middle of page 263. Okay, and we were just seeing, will any number go into 23, 27 and 36? 3 will go into 27, how many times? 9. 3 will go into 36, how many times? 12. Anything go into 9 and 12? 3. 3 will go into 9 3 times. 3 will go into 12 4 times. Nothing will go there. So this is going to be 3 pi over 4. 3/4 pi. Okay? Now, you didn't have to do it that way. You just could have, there's lots of ways you can go. But now I like to stop and pause, draw. You'll find that I'm really probably not very much of a visual learner, but pictures are important, I think, okay? So let's do our circle again. That's not a very good circle, but let's just imagine it is. And where are we with 135 degrees? Well, I know from here to here it's going to give me 90 degrees, and that would be 180, so I'm something between 90 and 180. Well, what is it? 135, let's just subtract that from, either subtract 90 from that. Let's do that, that's easy. 90 from that would be what? Say again? From 135. 45 degrees. Oh, we know where 45 is. That splits right down the middle, doesn't it? So there we are. There is your 135 degrees. Now, let's see, is that the same as 3/4 of a pi? Okay? 3/4 pi. Okay? There's pi fourths, pi halves, 3/4 pi. Yes, yes, yes. That's also 3 pi over 4. I like to check answers. Okay? I like to make sure I did it right. And you know what I like even more than that? I want you to check your answers and make sure you did it right. Now, did I tell y'all before what makes a good mathematician? In my mind, this is my theory. What was that? Lazy. Being a little bit lazy. Well, I'm not really all that great a mathematician, but I am lazy, okay? And therefore, I like, guess what the easiest papers for me to grade are? Perfect papers that I don't have to find how you made the mistake. I don't have to mark it wrong and write down the correct answer. I can just do check, check, check 100. I love doing those. They're easy. So I want you to have perfect papers so I don't have to do much work, okay? Watch out for me, okay? That's my goal, to get you to get perfect papers so I don't have to work that hard, okay? So do it. Check your answers. Make sure they make sense. Always, in any problem you do, does this make sense? Yeah, this makes perfect sense. All right. That's my technique. I don't memorize which one I put on top when I'm going this way or that way. Do the conversion. Okay? Now let's see how they did it. 135. They multiplied by that, which is the same thing we wound up with. Why? Because the degrees cancel out and you're left with radians. That's going to give you your answer. So they did the same thing we did, but they did it because they say, when you're doing this, you do that. You know, use your rule. Okay? And that gives you 3/4 pi. Same thing we got. Okay? Now, let's go back again in space. Okay? And wipe this one out. And let's do, yes?
You always use pi over 180?
Unless you use 180 over pi.
Yeah.
One or the other. That's the ratio you use, yeah.
You won't ever use 2 pi, like 360?
Why?
Always use,
That's more work. I'm too lazy for that. You can do it. He's a hard worker, I can tell, you know. Yeah, okay. No, that's the easiest ratio to do. Easy to remember, everything else. So let's do the B part, which is 540 degrees. Okay. Dot, dot, I mean space, blank, blank, blank. We're trying to get the radians. What do we do first? Okay, put the units in their place, and that happens to be radians over degrees. That way you can cancel out the degrees and leave radians right where you want it. Then you match the numbers with the units. And what are those? Second? Pi radians is the same as 180 degrees. So match the units with the numbers with the units, and now we go to town. Now, this one, I'm going to wipe out a 0 just to begin with. That's dividing by 10, both of those. That's easy. Anything that will go into 54 and 18? Second? 9. Okay, 9 will go into 54. How many times? 6 times. 9 will go into 18. 2 times. Ooh, anything go into 6 and 2? 2. So that'll be 3 and 1. Okay, so this gives us 3 pi radians. You don't have to put it over 1 if you don't want to. Well, let's check and make sure that's right. Okay, draw your little circle. I don't draw circles well, but pretend that's a circle. Okay, and 540 degrees. Well, that's one time around is going to be, it's what? Okay. How about half time around would be 180, okay. And then full time around would be 360. We're still not there. But another time around would be 720. That'd be too much. Go another 180. There you are. You're at, what do we do in radians? 1 pi, 2 pi, 3 pi. Yeah, same thing. 180, 180, 180, 1 pi, 2 pi, 3 pi. Yep, same thing. All right. Convinced of that? Let's watch how they did it. Well, I can just... Okay, 540 degrees. They just tell you what the answer is. I don't like that. I want you to figure out the answer. And what I would have done, rather than writing again, is done here. We'll do it times here. Match the units with the units. Degree on bottom, radians on top. Pi radians, 180 degrees. And then that gives you 3 pi radians. 180 into 540 is exactly 3. Okay. Now, they're moving to applications while they're skipping example 4. So let's back up a little bit and let's us do example. Whoa. Example. What is going on here? Okay. Example 4. Negative pi halves radians. We're trying to get that to convert to degrees. So what do we do first? Put units in their place, and what place will that be? Degrees on top, radians on the bottom. Very good. So the radians will cancel out. Now we match numbers with the units. What goes with degrees? 180 degrees is the same as pi radians. Perfect. Oh, look at here. The pi's are going to cancel out, which is too bad. I like pi, okay? And the 2 will go into 180. 90. And that will leave us with minus 90 degrees. It doesn't take much of a circle to remind us that's true, does it? Okay, what is minus pi halves radian? You go down 1 quadrant. There you are, minus pi halves. And that's also minus 90 degrees. Right? Yeah. Pretty easy. Right? Want to see if we can do the next one on the same page? Well, maybe. Yeah, we can. This time we have 2 radians. And if they hadn't said radians and just said 2, you knew it had to be radians, because if you don't have a unit there, it's radians. Multiply this by blank blank, and we're trying to get blank degrees. It's going to be a little squirrelier, right? What do we do first? Okay, a little louder. My hearing's so bad. Second? Degrees on top. Okay. I'm hard of hearing. That puts radians on the bottom. Okay? All right. That works. And then what numbers do we match with those units? 180 degrees is pi radians. Boo-hiss. Nothing to cancel out, divide out, or anything else. This is just 360 over pi degrees. Ew. But that's exactly the answer. 360 over pi degrees. And if you want to pull out your calculator and calculate that, they say that comes out to be about 114.59. Approximately 14.59. Now, how in the world they get 5 units of precision out of 1 unit of precision here, I don't know. But let's go back and remember. Remember, whatever your radius is, that amount of arc length is going to be 1 radian. So that's going to be just under 60. So 2 radians is just going to be just under 120. Yeah, that's just a little under 120. So yeah, it makes sense. Always make sure your answer makes sense. May not have an exact answer here, but you're in the right ballpark. If that had been 14 degrees, I would have been seriously doubting that's the right answer. Okay? Or 214 degrees. Nope, too far, way too far. 114 sounds about right. All right, any questions on that? And I think I mentioned to you before, but since at least one person wasn't here before, after every example they give, I'm pretty sure, there is what they call a checkpoint. Okay? That checkpoint is very similar to the example we just did. And so I say I recommend so highly that as soon as you're out of class and not in another class, and have a little bit of free time, go back and do the checkpoints that we just did the examples on. Okay, that makes what we just did in class yours. You know, you get to do it quickly, okay, right away. If you can't remember how to do it, if too much time has elapsed or you have to be totally confused, guess what? There's an audio video solution in English and Spanish at larsonprecalculus.com. Free website. You don't need a code, you don't need a pen. Just go to the website and you'll have to learn to navigate the website, but you can find it pretty easy. Y'all are good at navigating websites. I'm not, you know, too old for that. But I can do it. But anyway, do those soon. All right, any questions? All right, let's go on to Applications, okay. Here's one application that we use with degrees and radians, let's call it. The radian formula, if you remember, we define the radian as, or the number of radians, as the arc length subtended divided by the radius. That's what I just said, in that last example. 1 radian is 1 radius along the arc. A little bit less than 60 degrees, okay? So this is true. This is how we define a radian. It's the arc length divided by radius. And that's why it really doesn't have a unit. Because if the arc length is measured in centimeters, you measure the radius in centimeters. If it's in inches, you measure inches. If it's in furlongs, you measure furlongs. But you do the same. Okay. That can be used to measure the arc length of a circle. How? It's pretty simple. Arc length is S. So what do you need to do? Solve for S. Multiply both sides by R. So S equals R theta. Boy, pretty simple formula, right? So if your angle is, give me a number. 60 what? Degrees. Okay, 60 degrees. Multiply 60 degrees by your radius, right? What's wrong with that picture? Theta is in radians, not degrees. You can't use this formula with degrees, okay? It only works with radians. For a circle of radius r, a central angle theta, where theta is measured in radians and radians only, okay? Simple formula, but works only with theta in radians. Never will it work with theta in degrees, ever, okay? So if r is equal to 1, then S is equal to theta. Ooh, that's interesting. The only difference is 1 has a unit with it, inches, centimeters, or something, and then theta, S has that same unit, but the number is equal to the number of radians. Radian doesn't have a unit. Okay. The radian measure of theta equals the arc length only when the radius is 1. The radius of a circle is 1. Guess what we named that circle? Okay. Anyone know? Do y'all know the card game? That when you wind up with one card, you have to call out the word. Uno! Exactly. Okay. Uno means one in Spanish or somewhere, right? What word can we almost get out of that in English? Unit. We call that the unit circle if the radius is 1. Hang on to that thought. We're going to be dealing with unit circles really soon. Okay. So, here's a good example here. Example 5. Finding arc length. A circle has a radius of 4 inches. Find the length of the arc intercepted by a central angle of 240 degrees as shown here. Okay? You tell me how to do it. How do you find arc length? What symbol do we use for arc length? S is equal to, what formula do we have? R theta. Can you plug and chug? What would you get? What would you get? What's your radius? 4 inches. They couldn't put the units they should have. Okay. So you could do 4 inches times what? 240 degrees, I heard. Will that give you the right answer? Okay, now let's just imagine. Here's a circle. Can you guess that radius might be about 4 inches? Maybe a little bit bigger, something like that. Right? You're going to go 240 degrees around here, and that's going to give you 960 inches of arc length. 960 inches of arc length is 8 feet. Is it? Yeah, something like that. No, 80 feet. We have 80 feet of arc in that little circle. What's wrong with this picture? You can't use degrees in this formula. Theta is only in radians. So what's the first thing you got to do, folks? Convert 240 degrees to radians. Okay? And how do we do that? What's the first step? Radians over degrees, so the degrees will cancel out. And then you match. Pi radians is how much? 180 degrees. And now I do some divisions here. I can wipe out zeros right off the bat. Anything common between 24 and 18? 6. 6 will go into 24. 4 times. 6 will go into 18. 3 times. So that gives me, all right, so let me erase this error here, okay, and we'll write instead 3/4 pi. No, 4/3 pi. Y'all can't write, can you? Okay. 4 pi over 3. And that gives me 16 pi thirds, 16/3 pi. Okay? And that will be in inches. Keep your units. Okay? Now let's see. Does that make sense? Let me see. Pi is what? Approximate value for pi. 3.14. Let's just round that to 3. 3 over 3 is close to 1. A little bit more than 1. 16 times a little bit more than 1 is a little bit more than 16, right? So, would that be how many inches? If this is 4 inches radius here, would it be 16 inches to get down here? A lot better than 80 feet, okay? I think that's a lot closer. So that seems fairly reasonable. So let's see what answer they give. I think I need to erase some, don't I? Can I get away with erasing here? Y'all okay? Anyone need it longer? Okay. So let's see what they do. First thing you got to do is get those degrees to radians. You cannot use the formula S equal R theta with degrees. You got to get the radians. That gives you 4/3 pi radians. Good deal. Plug that in now. S is equal to 4 inches. They did left off the unit times 4/3 pi, and that gave you, I said, a little bit more than 16 inches. Good deal. That seems right. Okay. Make sense? Not quite 80 feet. Okay. Nowhere close. Okay. Any questions on that? Guess what you find next? Oh, wait. Note that the units for R determine the units for R theta because theta has no units, so that would be inches as well. We already said it, but they did. Then next you'll find another checkpoint. Okay, please do those as soon as you can. All right, here's another place that we use this periodically. The formula for the length of the circumference of a circular arc can help you analyze the motion of a particle moving at a constant speed along a circular path. Can anyone think of anything that would move along a circular path at a constant speed? Second, the moon going around the Earth? Very close. Not exact, but pretty close. The problem with that is the moon's orbit around the Earth is not quite circular, it's slightly elliptical, as is every planet going around the sun. They're never in circular orbits, they're always slightly off. But it gives you a good approximation. Okay? If I had a battery in it, and I had a second hand, it moves around the circle at a constant speed, doesn't it? Yeah, that's going to be the next problem. Okay? Okay. That's sort of an artificial one, but it is. Okay, so linear and angular speeds. Okay, think of this too. Any of you have central pivot irrigation systems for your grass? Okay, that usually goes at a fairly constant speed. There's lots of things that go like that. Consider a particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time, then the linear speed Anyone know what linear speed, sometimes we call it velocity, is? Little boy. Distance over time. So the distance you traveled with the arc length, the time was the time. Okay? So the linear speed would be arc length divided by time. S divided by t. Now, that's linear speed, distance over time. Meters per second, centimeters per second, inches per second, furlongs per fortnight, whatever you happen to be. Okay? Distance over time. Moreover, if theta is an angle in radian measure, corresponding to the arc length s, okay, which it always does, then the angular speed, and they use this little symbol here, don't call it a W. It looks sort of like a W, but that is the lowercase Greek omega. Uppercase omega looks like an upside down horseshoe. Lowercase omega is that thing that looks like a W. By the way, it's the last letter in the Greek alphabet. They don't have a Z, they have an omega. The angular speed, represented by omega of that particle, is the angular distance, the angle that's traveled in that time divided by the time. So it would be in radians per second. Understanding radians is not really a unit, it just has something to say. Per second is really what it is, but it's radians per second. So that's the angular speed. Now, since this is radians per second, that's your omega, and this is your linear speed, arc length per second, centimeters per second, whatever that would be. If you multiply this by r, since this is in radians, remember, in radians, okay, right here, in radian measure, okay, r times this will give you x. So r omega is v. So there's lots of little things you can do with that formula. Physicists do these little things, and most of you will continue and do physics, right? Aren't you either pre-engineering or math or something like that? Most of you? Yeah, you'll be seeing physics. Now, math majors don't have to do physics. All your pre-engineering pretty much do. If you're biomedical engineering, you have to do biology and physics, okay? But you got to do physics. So you'll be seeing this again, okay? So, here's another definition. A sector of a circle is the region bounded by two radii, there's a radius, okay, of the circle, and their intercepted arc, that's this. That is called the sector of the circle. The pink, or whatever color you call it, fuchsia, whatever that is. That is your sector of the circle, defined by the amount of angle that it sweeps there. Okay? Now, that's just a definition. Oh, Johnny come lately. Okay, Ryan is here. All right. So we're only missing Tiffany Nicole Fitz, whom we haven't seen from the beginning, Lindsay, and Stephanie. I think. Yep. Good attendance, folks. If I ever get to flashing through slides too quickly, most of the time I do way too much talking. Everybody can write, but if I do get to going too fast, stop me. You say, hey, slow down. Can you go back to the last one? I don't mind at all much. Okay. Okay? Everybody got it? Okay. So, here's a formula for the area of a sector of a circle. We just defined what that sector was. Here's how we find this area. 1/2 r squared theta. Now, like I said, I don't like memorizing anything. So I do a really lousy job memorizing. But here's one thing I do, okay? I try to make some sort of sense out of it so I don't have to memorize it. I can sort of reproduce it. First, I want to make sure the units are right. Remember, theta measured in what? Second?
Degrees.
Ooh, boy. Radians and radians only. These thetas here, we talked about in the last several examples, have to be in radians. Look right here, where theta is measured in radians. That's a dimensionless quantity. No dimensions to it. So R is going to be your length, some length, centimeters, inches, whatever you're measuring in. When you square that, you get a square centimeter, square inch, square mile, whatever. That, sure enough, is an area. So the units are right. So you got to have, the R has to be squared. Okay. Now, this is not really very precise. It's just something I use, especially when the picture looks like this. What does that almost look like? A triangle, a little bit like it, doesn't it? Okay. Now, the base of that triangle would be the radius, right? If that were a triangle, what would its area be? 1/2 the base times the height. Okay? Now, this doesn't fit exactly, but it helps me. That's where the 1/2 kind of comes from. Okay? The base is R. And the height, well, that's not real clear here, but it's not too far from being the arc length, which is r theta. So this is 1/2 r squared theta. Now that's not exact, but that's how I remember it. I do things like this because I don't memorize well. I do things to help me remember, even if they're not quite accurate. But you know that if they get me there, I'll excuse that for now. But of course, what you notice here, the big caveat, theta has to be in radians, only in radians. Oh, well then we missed the last two examples, in fact. So let's do example 6, okay? And that's a good old clock here, okay? The second hand of a clock okay, is 10.2 centimeters long. Okay. All right. 10.2 centimeters long. Shown in the figure at the right. So I'm going to try to draw a clock face. Okay. That's not a very good one. I always put the axis in there so I know what to go from. So let's see, this will be 1 and 3 and 6 and 9. I know that part, and this also 12. Not 1, but 0 and 12. And then we'll do 1 and 2 like this, and 4 and 5 like that, and 7 and 8 like that. These aren't exact, but you know, close. Not really very close, but 10 and 11 like that. Okay, so that's sort of my ugly clock face. Okay, and the second hand that's going around here, it turns clockwise for some strange reason, but never mind. Okay, that is 10.2 centimeters long. So that's my radius of this circle. Okay? Find the linear speed of the tip of that second hand. So what is the speed of that clock face, of the second hand going around the clock face? What? Can you do that? I can't put a speedometer on that and measure it. How can we do that? Okay. Oh, okay. I was going to say, we're missing. Oh, I'm sorry. I sort of blew something here. I got myself confused here. After we did linear and angular speeds, we were supposed to do this. I went on and did area of a sector. I said, this has nothing to do with area of a sector. Well, these two examples, 6 and 7, should have been after the last thing. So I've got it in the wrong order, but forgive me, I knew what I was doing. Okay, never mind. So, what did you say?
If we're doing linear speed, we'll be arc length divided by time.
Very good. So linear speed, velocity, is equal to arc length s divided by time t. Right? Very good. Except, how in the world do we determine what the arc length is? Or even the time is? Pick an arc length you know what time it is. On that clock face. I don't know what the arc length is here. I know that would be, that would be 1 hour, but that would be some fraction of an hour in seconds. This is the second hand moving here. But I do know the arc length of that, or even that, or something else. But let's do this one. That one, I know the arc length of that. What is that? The arc length.
360.
Say again?
360.
360 what? And are we using degree? No. Okay, so let's use
2 pi.
2 pi radians. Okay. So we know that the arc length could be 2 pi. And how long did it take me to get around there? Second hand going around the clock, how long? Say again? 60 minutes. Okay. It's the second hand. 60 seconds. Okay. So that takes 60 seconds. There's the arc. There's the speed right there. It would be 2 pi divided by 60, which would be pi over 30. And that would be inches, no, centimeters. Oh, wait. Y'all led me astray here. The arc length is not 2 pi. Well, yeah. Wait a minute. Yeah. Okay. No, the arc length is 2 pi r, right? You have to have a thing. And what's your radius? 10.7 or 2. What is that? I can't read my writing. 10.2. There it is. It's up there. 10.2 centimeters. And then that's my arc length. This is the theta. This r theta in radians. Okay. So this will be 20.4 pi divided by 60. Now I could do some divisions there, but it's not going to help much. Pull out your calculator and do it. And what do you get? This will be in centimeters per second, which is a good velocity. 1.07 centimeters per second. All right, good deal. That was that one, example 6, 1.07 centimeters per second. There is a checkpoint there, by the way. Now, I'm going to go back where I should have been last time. Okay. Let's do example 7 here. The blades of a wind turbine, I'll try to draw the wind turbine. Something like that. The blades of a wind turbine are 116 feet long, which is pretty long, folks. Have y'all seen any wind turbines? Okay, you don't have any around here. My wife had professional meetings in Salt Lake City, Utah, a few summers ago, and it happened to be the week between spring and summer term, I believe it was, something like that. So I got to go with her, and she was only going to be there a short time over the weekend, so we took most of that week off. And before her meetings, we drove around some of the area, and we were Montana or Wyoming one. It seems like we were in Montana. And we would drive past, and there'd be huge wind farms because it's just a lot of vacant land, really hilly and stuff like this. The farmer was down there cutting hay underneath the wind because they were way up in the sky like this. You could still do, so he was leasing his land and getting crop benefit from that and doing hay for his cattle or selling or whatever. So it's a pretty good deal. But huge wind farms. I mean, just dozens of them out there just whirling away, thinking free energy. I mean, you got to put the expense of investing in that, but the power source is free. I mean, there it is. Not a bad deal to do. So 116 foot, and they were long, so that's about right. Okay, the propeller rotates at 15 revolutions per minute. So this goes around here at 15 revolutions per minute. Now that has a shorthand abbreviation for it. Do you know what you call that? RPMs, exactly. So you could call this as 15 RPMs. That's not a mathematical or physics type thing, because revolutions isn't a unit, and M is usually meters, but this is revolution per minute, RPM. It's just a common name for that, okay? But I like to use revolution divided by minute, okay? Find the linear speed of the tip of the, no, I read the wrong problem. Find the angular speed of the propeller in radians per minute. So here we're given 15 revolutions per minute, and it says find, I've lost it now, the angular speed of the propeller in radians per minute. So what we're trying to get to, I'm going to put a conversion factor in here because I think that'll work for us. We want this to be radians per minute. Okay? Again, I'm going to use a conversion here. So the per minute stay the same, so we don't have to do a thing to the minutes. What we have to do is get revolutions to radians. So what unit goes where? Second? What unit would go where?
Only the radians on top.
Radians on top and revolutions on the bottom. Okay? Now let's take a simple revolution. Like one. One revolution of this around here is how many radians? What again? 2 pi, exactly. One time around is 2 pi radians. So there's our thing. 2 pi radians is one revolution. So here we have Lindsay. Okay. Now we're only missing Tiffany and Nicole Fitz, whom we haven't seen from the beginning, and Stephanie. Okay. Who was here for the previous time. So here we have 15 times 2 pi is pretty easy math. 30 pi radians per minute. Because the revolutions cancel out, you're left with radians per minute. That's the angular speed. Now, if you want to multiply that, it's going to be something a little bit more than 180 radians per minute. They don't do that. They leave it 30 pi. Perfectly fine. Okay, the B part says, find the linear speed of the tips of the blade. So now we're looking for this, the linear speed. Okay? And that would be measured in feet per minute. Okay? They didn't tell us what units to use, so we're going to use feet per minute. Okay? So what have you got to do with that? If you know you're traveling at a angular rate of 35 radians per minute, how do you get that to feet per minute? How do you go from radians to feet? Radians to distance, basically. Any ideas? Multiply by the radius. And that gets you 1 revolution. That's what we're dealing with, 1 revolution. That would be the arc length. Okay? So multiply this, omega times r. Don't remember we said that? That would be 116 feet times, this was our omega, by the way. Angular speed is omega, 30 pi. Okay? Now that's going to be some big old number. I can't, well, I could do it without too much problem. Pi, and that would be a 0, and that would be an 18, and that would be for 3,480. I hope I did it right. Someone check me on that. I believe that's right. Pi, multiply that by pi, and you get something on the order of, if you got a calculator, what you get? Second? I can't hear. It is right, okay. And multiply it by pi. 3,480 by pi. Say again? 33, you say? Yeah, that's what they had in the book too. That would be feet per minute. Whoa oldy here, you know. 15 revolutions per minute, that doesn't seem like that many. That's 1 revolution every 4 seconds, right? But with that long an arm, that thing's flying. I mean, that thing is moving fast. You don't want it. You want that to be way over the tractor top. You know, if you're baling hay under it, you don't want to be cut by that. 10,000, almost 11,000 feet per minute. Moving pretty fast. All right, good deal. Any questions on that? There is a checkpoint. Please do the checkpoints as soon as you can after class. Now, we'll pretend we just now got, how are we doing on time? I haven't even pulled my watch out. Second? A minute? 10 minutes. That's much better. Okay. All right. Good deal. All right. Let's go to our, all right. This is where we want to go. We did this back. We should have done that earlier. Here is the example 8 for the area of a sector of a circle. A sprinkler on a golf course fairway sprays water over a distance of 70 feet and rotates through an angle of 120 degrees. Find the area of the fairway watered by that sprinkler. So here we have, I can't draw as pretty as they do, but here we have the sprinkler head, and it's spraying from here to here. They said about 120 degrees. Let's just guess that's true. 120 degrees. And it sprays for 70 feet. It only goes about that far. You hear it? Okay, there it goes. Okay. So that's 70 feet. So what is the area here that it can cover? Got any formula that might work? Oh, yes. What is it? A is equal to 1/2 r squared theta. Okay. I'm going to guess this is my r here, the radius. Do we have a theta? What is it? Second? Yeah, we have a degree theta. Can we use it? No, we can't. So what was the first thing we got to do? Convert it, okay? So 120 degrees times a blank blank is equal to blank radians, because it's got to be in radians. What unit do I put where? Radians on top, degrees on the bottom, match numbers with units. Pi radians is 180 degrees. And then I know the zeros will go out. What will go into 12 and 18? 6. So that will go 2 and 3. So that will be 2 pi over 3 radians. Okay? So let's take our area. Would then be 70 or 1/2 of 70 squared. That'd be 4,900 times 2 pi over 3. Okay? Well, I can do 2 into, well, I'm going to do 2 into pi. 2 into 2. That'll be easy. And that'll be 4,900 pi divided by 3. And I'll count on somebody with a calculator telling me what that will come out being. The units are going to be feet squared, because the only thing with units is the radius of 70 feet. You squared it, so 70 square feet. Ooh, a little slower. 5,000. 131 square feet. All right. How'd the book do? Oh, that's where you looked, wasn't it? No, never mind. Okay. I thought so. Okay. Good deal. See how it works? Can't use 120 degrees. Never can use. With these formulas, you have to use radians. Okay. There is a checkpoint there too. And there's audio-video solution for that checkpoint if you can't get it to work out. All right. Now, we do have some vocabulary here. Do we have time to do it? Okay, let's see if we can get this done. Vocabulary here. Number one, two angles that have the same initial and terminal sides are blank. Coterminal angles. Perfect. Number two, one blank is the measure of the central angle that intercepts an arc equal in length to the radius of the circle. What?
Sector.
I can't hear.
Sector.
Sector? One blank is the measure of the central angle. It's an angle measure.
Degrees.
No, not degrees. Radians, the other thing. That's why it has to do with the radius. It's a radian. Okay, number three. Two positive angles that have a sum of pi halves are blank angles. Complementary angles, and two positive angles that have a sum of pi are supplementary angles. Number four, the angle measure that is equivalent to the rotation of 1/360th of a complete revolution about an angle's vertex is 1. It's your turn now. 1/360th of a revolution. That would be 1 degree. That's your degree. Okay. Number five. The blank speed of a particle is the ratio of the arc length divided by to the elapsed time. That's the linear speed. And the blank speed of a particle is the ratio of the change of the central angle to the elapsed time. Angular speed. And number six, the area A of a sector of a circle with radius r and central angle theta, where theta is measured in radians, is given by the formula. That's it. Perfect. Okay, homework exercises here. Do either 7 or 9, or both if you choose. Now, why do I give odd problems? There's two reasons. One reason, the answer's in the back. So do the problem, see if you get the right answer. If you didn't get the right answer, you can't figure out why you didn't get the right answer. Guess what, team? This is another thing this book has that no other book I've ever taught from has. Look at the top here. See calcchat.com for tutorial help and worked out solutions to the odd number exercises. So they have, here's another free website, no codes, nothing required. Just go to it, calcchat.com. Okay? So all the odds are there. So if you can't get the answer in the back, go to calcchat.com. Do number 11. Do number 13. They have 2 parts each. Do number 15. Now 15 has something else about it. If you notice 15 here in the book, there's two things. It has a little QR code right above it, and it's also in red. That red means, and the QR code means, that you can go to another website. It's called calcview.com. This is calcchat.com. That's calcview.com. Okay? If you have a cell phone, you can just pick up the QR code, and it takes you to that website. Okay? So there's another. These, again, more information is given there. And then do either 17 or 19. They're both at CalcChat. 17's at CalcView. Do either 21 or 23. They're both at CalcChat. Do 25, it's at CalcChat. Do 27, it's at CalcChat. Do 29, it's both at CalcChat and CalcView. And do either 31 or 33. They're both at CalcChat. 33's at CalcView. Do 35, it's at CalcChat and View. Do 37, it's at CalcChat and CalcView. Do either 39 or 41 or both. They're both at CalcChat, neither at CalcView. 43 or 45, they're both at CalcChat. Now 47, we didn't do one just like that, but you should be able to figure it out. If you can't, and you can't get it through CalcChat or well, it doesn't have CalcView, If you can't figure it out, come to class and bring it. 47, same thing with 49. 51's at CalcChat and CalcView. 53's at CalcChat. 55's at CalcChat. 57's at both CalcChat and CalcView. 59's at CalcChat. Okay, I really don't like those as much as the others. And then an earth, space, science type thing, you can do either do 61 if you, it's not that bad, and then 60. Do any of the odds, 63 through 69. They should all be at CalcChat. There's exploration, true, false. I won't ask you any like this on a test, but it's still not a bad idea to think through them. 71 or 73, they should both be at CalcChat. If you want to do that writing exercise at 75, I doubt if it's CalcChat, but you can check and see. Thinking about 77 or 79, that's up to you. 79 is proof. I don't know if they're all at CalcChat or not. Next time we'll get started on 4.2. Any questions? Good deal. All right. Yes. I'll go back to here. Okay, that one. Okay. Okay. And I'll add one more up here. Linear speed is R omega. I did that because it comes from this. So R times theta is S, and S divided by T.
R times theta is this?
R times theta is S, right? Okay. Arc length is radius times angle. So if you multiply this by R, you get S. So R times omega is that is linear speed.
So the whole point, I know it ain't last time.
Second, no, it's all for your practice. Yeah. Your cultural enlightenment. Okay, right. Good deal. All right. Any further questions?